Alright, so I'm going to walk through how I did these tension calculations. So basically what I was trying to figure out here is, how strong does a servo motor have to be able to tension these strings and bend them when I push on the pedal. So first step is I found some strings. So these are not actually the ones that I bought, but it turns out that D'Addario puts out a lot of technical information about their strings, so it was easier to do my calculations with these rather than the set of Ernie Ball strings that I actually bought for the guitar. I imagine the results are going to be pretty similar, but I started with these. So basically I looked up a set of E9 pedal steel strings on D'Addario's website. I came across these, and the next step is I got to calculate the tension force on each one. So if you open this tab here, they actually show you the tension force, which is pretty cool. I actually found this much later after I'd already done all the calculations, but they give you the names of the strings here, the note of each one, the diameter of each wire, and then the tension. So you can see the tension goes up to 31.24 pounds at the most. So yeah, that's pretty good reference information. Now the other thing I found is from Googling around, not this, I found this guide. So this is a guide that D'Addario put out at some point. This is a technical reference with all of the unit weights for their strings and the formula that you can use to calculate string tension from that. And so another thing you could do, if you want to do the calculation manually rather than just taking these tension values that they give you, you can go in this guide and actually find the part number for the string that you're interested in, and then you get this unit weight, and basically the unit weight you can use to calculate the tension force on that string when it's tuned to a particular note. And the formula you use, so they're showing this formula here, which is unit weight times 2LF squared over 386.4. And then they say convert to newtons, multiplied by 444.45. So what this is, this formula is really the formula for the frequency of a string in tension, the natural frequency of a string in tension. Rearranged. So they took this standard, physics formula, which is frequency equals 1/2 times the length of the string, the free length that's able to vibrate, times the square root of T, which is the tension force, over mu, which in this case is the unit weight. And so this mu is the same as the unit weight that they're showing here in this formula. So if you rearrange this frequency formula, you'll actually get this this tension formula here. And because SI units would give you newtons, I think this 386.4 is just a constant that they came up with to give you the result in pounds, if I remember correctly. And so you would just take these unit weight values. So that's exactly what I did. So when I did my string tension calculations, basically I started with, just ignore everything below here for now. Just focusing on this top section, I basically took all the 10 strings. I noted what is the open pitch of the string when you tune it to the E9th tuning for a pedal steel. Let me zoom in a little bit. So you got the open pitch and then the octave number. So there's actually a standard, so every pitch actually has a standard frequency and note name and octave number. And there's actually a chart for that, which I'm going to find here. Yeah, frequency tables. think this is the one I used. I used this other one because it's got more significant figures. Yeah, so this is basically the scale of every note, name, and octave all the way up from 0 to 9. You know, so this is like basically every pitch from 16.351 hertz all the way up to 15,804.264 hertz. So basically, you know, 16 up to 15 kilohertz, 16 hertz up to 15 kilohertz, which is roughly the range of human hearing. I think it's 2 kilohertz to 20 kilohertz is the range of human hearing. So this is like every pitch, and so they give you the frequency and with 3 decimal places and the octave number. So I basically just matched up. I found all the string pitches for the set of strings that I had based on the pack of strings from D'Addario and Ernie Ball, and I also and then I just copied down the frequency here. And so basically these are the octave numbers and these are all the frequencies in the normal open tuning for each string. And then I just had some notes here about whether it's wound or plain steel because I wanted to see if that might affect my calculations. And yeah, material. And then basically I tried to look up the part numbers for each string in that D'Addario guide. So I was able to find these plain wound ones, so PLO 13 to PLO 20. You know, so here's PLO 13, you know, that one's there. PLO 20 and the other ones. I was not able to find all of them in here, but I found stuff that was close. So PSG, I'm not sure what all these letters mean, but PSG seems to be the same as XSG in this guide. So I took anything that said PSG in this D'Addario pack. I just matched up with XSG. I don't think there's text in this, so I can't search it. But anyway, they're in here somewhere, the XSGs. So basically I looked those up, found the you know, the thicknesses are listed on the pack. So I have those and then converted those to meters just to be in standard SI units. And I got the unit weight from the from D'Addario, from that guide, and then calculated the mass per unit length just in kilograms per meter instead of pound mass per inch. And then the scale length, and by the way, I'm just noting what the symbols are in the formula for each column here. So this is F, this is mu, this is big L, and this is big T. And so big L is the length, which I'm using as the scale length. So the term scale length for a pedal steel for any guitar is the free vibrating distance. So it's basically from nut to the bridge, from the nut to the bridge, the free vibrating length of the string. So I just took that and this 24.25 I got from a pedal steel guide online. Basically, I've seen that most of the pedal steel guitars out there have a scale length of 22.25 inches or 24.25 inches. Some are a little more, a little less, but this seems to be the standard, so that's what I'm using. Convert it to meters, and then I calculate tension here using that formula. And this looks, this is the same formula that's in the D'Addario guide because I also rearranged it to be able to calculate tension force. So now I have that in newtons, convert it to pounds, and so this is the number of pounds of tension under normal conditions for each string. And if you're wondering, did my calculations come out right? This is these are the values listed on D'Addario's website for that pack of strings right here. And so I basically took that and I just compared those two down here. And so here's a graph of comparing my calculation to D'Addario's. And all of the plain strings are exactly the same, so my math was right. And all of the wound strings are a little bit off. My calculation looks like it was a little higher than the D'Addario calculation, their reported value, which actually makes perfect sense. Which is the reason why I wanted to note which strings were wound and which ones weren't, because when you're looking at the tension of a material, the formula that we're using is assuming that it's a solid cylindrical cross-section, circular cross-section, but the wound strings have another circular cross-section wire wound around the core, and so it's not exactly a circular cross-section. And so the effect that would have is the wound part of the string on the outside is not exerting as much tension on the string as the core is, because with the core you're directly stretching that material, whereas the wound part you're simply separating the windings. It's as if you took a wound up spring and you kind of you pulled it and you're separating the takes a lot less force to separate those coils from each other and stretch the spring than it would to actually take the wire itself and try to stretch the wire. And so that's why so when I calculated, assuming that the whole string is solid, I'm getting a higher tension value than when D'Addario calculates it, and they're taking into account, I'm assuming, the effect of that winding. So that actually makes perfect sense. So what I'm trying to figure out here is, what is the torque that I need to get on a servo motor to be able to very easily, so it's not too much work for the servo, very easily tension and detension these strings. And so now I have a force value, and now I'm calculating what is the torque required at a particular moment arm. So I have to figure out what's the moment arm that I'm going to use to transfer from the servo shaft over to whatever's pulling on the string itself. So that's something that's not determined yet. But for this calculation, it looks like I assumed 20 millimeters. It looks like I'm assuming something here. Yeah, so I'm setting a moment arm. So I was playing with different distances. So, and ultimately I was trying to figure out another way to ask the question is, what's the moment arm that I need if I have these servos that I'm going to use and they have a certain torque, stall torque, what is the moment arm that I would need to be able to keep the torque that the servo is actually expected to exert well below its stall torque? And so I tried different moment arm values. Here I'm looking at 6.4. So 6.4 is used in all of these calculations here. So I'm just taking the I'm taking the tension in newtons for each string, multiplying by the moment arm. So this gives us the torque required at that moment arm distance. And now the thing is, I'm using a counterweight, which is a spring. So I'm using springs to act as a counterweight so that when we're in the normal tuning of each string, the servo is not exerting any force. Ideally, it'll be a perfectly balanced, perfect force balance, and the servo will have zero torque on it. And it'll only have torque when you want to either bend a string up or down. So what I actually need to calculate is, what is the delta torque in that each servo has to exert to be able to move a string from the open tuning either up a whole step or down a whole step, which is the maximum range I would need to adjust. And so basically I'm calculating that, but in this case this is the open tuning state, so it'll be 0 because I'm not actually changing anything in the open state. And then I'm also putting a 2x safety factor just to make sure that my servo, I'm not expecting the servo to be anywhere close to its stall torque. And so that's the sequence of the calculation. And the reason I have all these sections is because I did that in each state. So I did that in the open string state, then I did it a half a step up, whole step up, half step down, and whole step down. And so you can imagine that the worst case torque that the servo would need to handle would be a whole step up, because that's the maximum additional tension that I would have to have the servo put on each string that I'm trying to bend. And so my worst case torque, that's why I have the worst case torque I'm looking at, is in that section there. And it's also going to be on the top string here, the first string in the list, because that one had the most force on it to begin with. And so we get 46, looks like 0.462, and that's in Newton meters, I believe. That is in Newton meters. And then that value, yeah, so basically I calculate that value, and then I said, okay, what moment arm do I need to make sure that that torque, well, no, that's the torque that I calculate. That's the max torque that I calculate. So then I went to the servos. Okay, so the servos I bought, let me see if they're in here. Yeah. So these servos are, let's see, these are the Tower Pro MG996R hobby servos with metal gears. The ones I bought are actually knockoffs. I think I got this pack. No, I didn't get this pack, but I got something similar to this from Amazon. They're knockoffs, but I'm using the values from the actual authentic Tower Pro website here as a guide. So it's saying that the stall torque at 6 volts, you know, I don't remember which one of these I used, but I took one of these and basically converted it to Newton meters from kilogram centimeters. And yeah, so I did it at both voltages. So the 9.4 and the 11 turns out to be 0.922 and 1.079. And so I took the worst case of these. So if I'm driving the servo with 5 volts, then I would get this stall torque 0.922, and I just divided that by 2 to get my 2x safety factor. And so now this 0.461, this is the target torque that I don't want to go over. So basically I need a moment arm that will make sure that my torque never goes over 0.461 Newton meters, almost half a Newton meter. And so I played around with it and basically found that 6.4 was the maximum, or the smallest moment arm that I would need to make sure that the torque never goes over 0.461. And so what is 6.4 millimeters for those of us who are not in a millimeter country? Let's see what that comes out to. 6.4, 25.4. And that's 0.25. So it's about a 1/4 inch. That is not a lot. 1/4 inch long moment arm is the smallest moment arm that I need to make sure that my torque doesn't go above half of the stall torque of the motor at the lower voltage level. So I have a good amount of wiggle room there. And a 1/4 inch moment arm is not much at all. That's very, very little. So it's entirely possible that I'll be well below that. So this is good news. So this basically means that this motor is going to work, should work. And yeah. So then the other thing is I had to figure out is what do I attach to this spline of this motor to be able to drive the string. And so this is an option here. These are off the shelf. Looks like aluminum 25T. That's the 25 tooth spline horns that you can put on the servo, and they have a set screw there that'll squeeze it nice. So I like the design of these. The only problem is the first hole out here. What does it say? Hole centers are at 20 and 24 millimeters from the servo output. So this one's 20 millimeters from the center. So basically, if you go to the calculation here, you're losing. It's almost as if you're losing 20 millimeters of moment arm, because in this case, because now you're expecting the servo to rotate here, and you're trying to pull the string at a distance of 20 millimeters. So so now the string is actually exerting more torque on the servo motor than it needs to. So the design goal here should be for the string to be as close to the let's say the tangent pull position of the string relative to the center of the servo shaft should be as close to the center of that servo shaft as possible. So it's not ideal that these horns here go out to 20 millimeters. Maybe I can attach the string to this little hole here and be closer, but basically I need to make up for that 20 millimeter arm with a larger moment arm elsewhere in the system. And so that's where those fingers come in on the tailpiece, or on the bridge or the saddle, whatever you want to call it, that I showed before. Alright, so I think that's basically all there is to show in this document here. And then I got the resources here that I used, a couple links. So I'll include all the useful links here. And then I just had a note here to remind myself to consider the reduction in spring force as the string is pulled. So the reason I have this is because the spring that I'm going to use as the counterweight, as we tension the guitar string, that spring is going to relax. And since springs have a linear relationship between force and stretch distance, that extension spring is going to exert less and less force as the servo is exerting more and more force on the guitar string. And so the effect of that is the amount of force, normally the amount of force that the servo would have to exert on the guitar string would be linear as you pull it more. But in this case, it's actually going to be nonlinear. It's going to ramp up faster than it would in the linear case, because the counterbalance that not only is the string being tensioned more, and so the servo has to do more work to pull on it, but the counterweight is actually dropping off as that's happening. So I had to I made a note to factor that in to see if that would throw my torque value over the stall torque, just to make sure that doesn't have too much of a negative effect. So I might take a look at that. I don't expect it to have a huge impact, especially if the spring has a very shallow spring rate. If the stiffness of the spring is low, but there's a lot of preload. So that's the ideal situation here. The way to prevent that issue from happening is to choose springs, counterweight springs, that will have a very shallow stiffness line, and that would be preloaded a lot. So basically, for every millimeter of change in stretch of the spring, there's a very you want the smallest possible change in the force that the spring is exerting. So you want a low stiffness spring, but you want a high preload so you can get up to that force value that the string is going to exert on the motor, so that you can balance it. So as long as you have a spring with those properties, then this issue shouldn't cause too much of a problem. So I'm probably going to not look at that yet, and I already bought the servos. I think they're going to be fine, so I'm going to do a test, see how it works before I spend too much more time doing analysis paralysis. So there's the string calculations.